All right, so this is going to be lesson 2 of the electrical principles for mechanical people. We're getting into both DC and AC today. We're also going to do a little bit of review from 2 weeks ago. All right, so again, the caveat for this is I'm going very fast. We've got about another semester or so crammed into this. These are very high level concepts. It's just mostly there so that you get an understanding so that you can talk to other people. There is actually homework. I did mean to mention that. So as you can see, I put the address for what is called the Magnetic River. This is from 1975. It's up on YouTube. This is what it looks like. You just click on one of these. I can't tell you how many times I've watched his videos. He's got several up there. They're all really good, really easily explained, and he does a great job of showing you visual concepts because he starts from this is a magnet all the way to this is how we make things float, all the way to this is how a motor works. So at some point in time, I highly recommend going and watching that before next week or the next lesson or whatnot. Like I said, I think there's 7 videos total, but specifically the magnetic river would be very helpful, especially after you listen to this lesson. The one caveat I do got to say is he uses the word aluminium because he's from England or something. I don't remember where here in America we use the word aluminum. And it took me once or twice to kind of recognize that.
Realize what he's saying.
Exactly. So aluminium is aluminum.
Aluminum.
Spelled different in different countries. So
pronounced differently.
Exactly. All right. So structure of an atom, proton, neutrons in the middle, electrons floating around very rapidly on the outside, which is the review. So if an electron goes from here to here to here to here, that is called electricity. That's the concept. Again, the magnet, and the copper wire. If I bring this negative side to this side of the copper wire, where are the electrons on the copper wire flowing?
They go to the right. Yeah. So like away from it. Sorry.
Yep, you're good. So current would technically be flowing in that direction. Tracking so far?
Yes.
Because I wanted to refresh on that because we're going to need it. All right. And again, I've kind of kept these in here just so that you can snip it if you need to. There are people on YouTube or whatnot. I'm not going to go through that again. So let's do some basic concept math. This is kind of a leftover of the last lesson. Same voltages, same concepts. So if you got 28 volts, 56 watts on a DC circuit, how many amps are flowing right here on this part of the wire? Magnitude. Oh, there we go. Yeah, there's the equation. Watts is equal to volts divided by amps.
Yeah, it's 2 amps.
Correct. And in order to use a multimeter to measure that, we have to get the multimeter into the circuit. So the amps go through the multimeter and out. Do you want to kind of refresh your mind on that one? All right. So what would be the voltage on the high side of this lamp right here? If I were measuring to ground. If I were measuring to the other side of the battery, we'll put it that way. There are 2 loads here. Keep that in mind.
I got the total resistance. Each one is 7. So is it 14?
Taken on the high side of this lamp.
Oh, okay. So I'm trying to think in my head. So because it's before, is it the total, which is 28? And then
Correct.
After it, the second, between the two is 14. And then after is 7.
So close. It is actually 0.
0.
So the reason for that is there is 0 resistance, essentially, from this side of the battery all the way to here. Okay, it's just copper wire. Assume no resistance.
Mm-hmm.
So if I were to take a measurement from here to the opposite side of the battery, I would read the full battery potential, the full battery voltage. And
Okay.
you'll hear me start to use those words interchangeably, potential and voltage. It's literally the same thing. So.
Okay.
All right. So if you've got 2 loads and the loads are equal, assuming resistance is equal between the 2, half of the voltage is going to drop across the first load, and the other half of the voltage is going to drop across the second load.
Oh, don't think so. the fact that the resistance is at 7 at both of them doesn't mean that you're halving the voltage again after the second drop. That's what you said. Like, is that the way you say it? Like,
Yes,
think about it as like the first one is the first half drop, and then you're dropping it all the way so that whenever you are trying to, like you're saying, read the voltage, if if you put if you put the like meter from after both drops and before both drops, you'll get 28 voltage because you're seeing 0 after both, right? Does that make,
exactly.
is that okay? So then if you put that same thing where the 0 voltage is after both drops and 1 in between them is why you'll see 14, because the voltage dropped once from the resistance and then dropped another. Is that the concept?
That is exactly accurate. Yes.
Okay, that makes
All right.
sense.
But I'm glad that makes sense, because my next question, if I put a multimeter from this point here to this point here, what voltage am I going to read?
You read the difference, I'm assuming, so that's 14.
Yes, you would read the difference in potential between the 2 points, which is 14. Because 28 minus 14 is 14. Exactly.
Okay.
All right. So if we got 2 amps going down this conductor and going through this lamp, how many amps have we got coming on this part of the conductor? So it's just like water flow. Remember, if we have water flowing through a water hose and we're going through a valve that, a valve that's half closed, assuming we have two gallons per minute coming through here at 28 psi, we got a valve that's half closed. Are we still going to have the same amount of gallons per minute coming out, just at a lower pressure?
No.
The amperage actually doesn't change.
Oh, it doesn't change?
Yeah, because you're not increasing or decreasing the quantity of electrons flowing through this conductor. Just like you're not increasing or decreasing the volume of water going through a water hose.
Gotcha. Just because the voltage is going down doesn't mean that the amps are like the amount of the current going through is going down.
Correct. Yeah.
Okay.
Yeah, because the amps don't change in a series circuit like this. The voltage will change, because that's what's pushing the amps along.
Okay. So math, if you're doing it like mathematically, is it because like you're still doing the V or E equals IR, and V is still 14 and R would be 7 because you like just passed 7 resistance, which would make current still 2? Like, is there a mathematical way to like understand like that's why that is? Or is that not how
Yeah,
it works?
no, there is actually. Let's see. You said this was 7 ohms, right?
Yeah, both are 7.
Ohms. I don't have the little horseshoe on hand, but let's just say it's 7 ohms here. 7 ohms there. All right, so that's 14 ohms total. So yes, you would start at the source and say 28 is equal to I times 14. And then 28 divided by 14 is equal to 2. So the total number of ohms, the total resistance, is going to dictate how many amps start coming out of this battery as soon as you close that circuit, this switch. It's going to go, I've got 14 ohms. I'm at a potential of 28 volts. That means I need to push 2 amps down this line. And when you start seeing that quantity of electrons going down, that quantity is not going to change throughout this series circuit. And we'll see 2 amps coming back into this side of the battery. Because remember, amps is a quantity of electrons flowing past a certain point per second.
Gotcha. The ohms is just it's restricting it's restricting the flow though, correct?
Correct.
Which is what's making like you're still I don't know if I 100% get that concept because I thought that like if you're restricting it, I know like pressure. Well, if you're restricting something, doesn't the pressure go up and your
Uh,
flow decreases? Isn't that like how that works?
so yes, in the water world, and that's why it's analogous and not equal,
Okay.
meaning it's similar. You can think of this like the water flow. However, it's not exactly like water flow.
Okay.
The idea is, if you have a battery here, you've got voltage here, and you've got two valves, the pressure is going to drop across each valve, and then you're just going to get water coming out with minimal pressure. It's the concept.
Gotcha. But you will
Just
still have eventually the same amount of water.
exactly the same
Okay.
volume of water passing a certain point is still the same, just
Okay.
not as fast.
Okay. That that makes more sense.
Okay. So we've got that. So that's a series circuit. This one you won't ever come across. This is like a maybe 2% chance that you would ever come across a series circuit. You will be using mostly parallel circuits
Okay.
because it's like lights in a building. They're not series; they're all in parallel. You'll see that here in a second. So same numbers. How many amps have I got going through here?
Still 2.
Yes. We'll go ahead and finish that out. How many have I got coming in here?
2.
Yes. So if these loads are the same, how many amps have I got going down this branch, and how many amps have I got going down this branch?
I feel like this is a trick question, but I'm gonna say 1 on each of them.
It is not a trick question, actually. The resistance is equal. So if you had water flowing down this pipe and you had two valves equally restricted, well, the water's going to want to go down each pipe, right?
Mhm.
And it's going to go in the same quantity, volume, and speed through each pipe. So yeah, it's 1 amp down each one of these leads.
Okay.
Right? So on my voltage meter, if I put one here to the battery, what am I going to be reading? So if I were to put a multimeter touching this side of the battery and this side of the battery, what would I read?
28.
28 volts, yes. So electrically, since this is all conductor, there is essentially no difference than if I were to touch it here versus here on the battery itself.
Which mean it'd still be 28.
Exactly. What about here? What if I were to measure there to the other end of the battery?
I feel like it would still be 28.
It would be. That's exactly right. Because there's essentially no electrical difference between here and this side of the battery since this is all conductor.
Okay.
Okay, it's just you can picture it as one big old chunk of copper.
Okay.
Right. So what about here to the other side, to this side of the battery?
Is it 0?
It is, yes.
And
Because
it's the same reason because it's like a giant chunk of copper, so think of the whole thing as 0.
exactly, it'd be like
Okay.
putting both leads of the multimeter right here on the battery. Like there is no potential difference if you're touching the same piece of metal, right?
Correct. That makes sense. Yeah.
Okay. All right. So what about right here?
I would
That,
still say 0.
yep, you're right. You're right. And for those, let's see if I can do this. And for those who are in college or trying to still understand this, a quick, easy concept check, just like I should have. All right. So on a series circuit, current's always the same. Voltage is what drops. What is tricky, we'll put it that way. Voltage is what changes. On a parallel circuit, current can change through each load, but is still the same going back. Voltage drops equally across the loads if they're in this configuration. So current same, voltage changes, current changes, voltage is the same. super simple, super summarized, like this is the base concept and you'll grow from there, but that's essentially what this amounts to. All right, on the graphing.
Does the resistance like are you not worried about the resistance like doing the resistance on the parallel circuit?
No, because 95% of the time the resistance is all going to be the same, or at least relatively close enough.
Gotcha.
But even then, the only difference that I would be concerned about in the real world is making sure my conductors are sized accordingly. Because if I've got one massive load, 50 horsepower motor in parallel with like a light bulb, well, obviously the 50 horsepower motor is going to need a lot larger conductor than the light bulb. I would never do such a thing, but should that ever occur, that's how that works.
Okay.
Good question. Yeah, that's a good question. But most of the time, like the lights, like this is a lighting circuit to me, like in a building, all the lights are going to be the same or relatively close.
Gotcha. But when you're doing when it's being wired up, it is going to be like lights would be done in parallel. Is that kind of what you're getting at? But
That
and
is
then
exactly
and they will all be the same. Like hence why you're saying like you don't typically see stuff in series.
correct. Yeah, the
Okay.
only time I've ever come across anything in series is the lights for a runway, like on a airport. But that's a whole different story. That's a whole new design we're not going to get into. That's the only time I've ever seen anything really in series like that.
Gotcha.
Which is
Just know
really cool.
typically it's done in parallel.
Exactly.
Okay.
So yeah. All right. So on a graph, what do you think a DC circuit's going to look like? Is it going to be squiggly line, straight line? Like, what's your picture of this?
I feel like DC circuit would be a straight line.
So choosing a random location, something like that, right?
Yeah.
And for the most part, you would be correct. That is good enough for an answer for the industry we're in. Sometimes, and you specifically won't actually need this knowledge, but sometimes it can actually look like this, where it's not exactly straight. Okay. The idea of this is it's all above 0 volts or all below 0 volts because you can have a negative voltage, which we're not going to get into here. But the idea is it doesn't have to be a perfect, exact straight line. It can be slightly squiggly like this. It is still considered a DC circuit. Okay. The reason I go into that is because of this trace. This is an AC circuit. It intentionally goes up, intentionally goes down. And obviously, that's a horrible drawing, but that's the idea. Everybody's seen a sine wave before, right? Or you have seen a sine wave, I should say.
Yeah.
Here we go. All right. So let me give you a little bit of history lesson. In 1893, Chicago World's Fair, there were two people that bid on the lighting at that fair. It was Thomas Edison and Westinghouse. Right. Back then, this is still like around the time of Nikola Tesla when he was still young. This is still when electricity was still relatively new. Not a whole lot of people had it. And at the time, we understood and knew what AC circuits were, a alternating current, AC, instead of DC circuits, direct current. Hence this is only going one way in the positive direction. And this is alternating into the positive and negative directions. So when Edison and Westinghouse bid on this, Edison, who was a DC proponent, like that's what he thought the world was going to go to was DC, he had to bid $554,000. And Westinghouse, who was an AC proponent, knowing that this is the direction we would have to go if we wanted long distance runs, bid a lot less. The primary driving factor, from my understanding, was the sheer amount of copper. So remember last lesson when I told you, if you have a water hose that is 2 miles long, you're not going to have the same pressure at the end as you did at the beginning, right? Even though there's no valves, no tangible resistance, you're still going to lose pressure across those 2 miles because of the distance and the inherent resistance of the water hose itself. Right? So technically speaking, yes, copper and aluminum have inherent resistances. And when we were talking up here, I said assume there is no resistance. Well, technically there is, but on short circuits, it's
Negligible.
it's completely negligible. Exactly. When you're getting into larger buildings, then you kind of got to look at it. Like if you're getting into high rises or whatnot, well, you've got to go up 30, 40, 50 stories, and that's 300, 450, 500 feet, somewhere around there. Once you get it to like 150, 200 feet, that's when you start kind of worry about it. Whereas that's analogous to like 300 feet on a water hose. That's kind of, okay, you're going to start losing pressure at that distance. When Westinghouse won this, that's when AC, alternating current concepts, really took off. That's when people really started to see the benefits, the cost benefits, the savings, the distance capable of AC circuits. And that's when Edison's DC push really kind of took a fatal blow and was like, okay, we're not going to be able to do this. Now, granted, he continued to fight for DC because there's a whole lot of stuff I'm not going to go into, but Westinghouse knew this was the direction we were headed in. The reason Westinghouse knew this was going to work is because if you have a long distance, you want less current and higher voltage. Because if you have higher pressure, if you have the more water flowing through the water hose, the more resistance is going to increase. But if you can increase the pressure and decrease the water flowing through it, you're going to decrease the effect that resistance has on it. And we'll see that math here in just a second. I know I'm kind of throwing a lot out there right now, but we've got to understand the concept of a transformer first so that we can get into why AC matters. In short, this is what all transformers look like on the inside. For all the college kids and whatnot, you're going to need this equation here. For all of the consulting engineers, whatnot, this is going to be your world right there. What this is saying is, look, if you have AC current going into these coils, which you can also see here, a whole bunch of coils, you're going to have a different amount of voltage and current coming out of the other side. And that's what this equation expresses right here. And this is what a transformer looks like what would be in your microwave or something, or control power transformer. All right, mathematically speaking, a 2-to-1 transformer, meaning for every 2 coils over here, you got 1 coil over here. If you got 480 VAC at 2 amps, you're going to have 240 VAC on the secondary and 4 amps coming out. So the next math problem you have is on a 50 kVA 480 to 240 single phase transformer. How much primary current do I have? How much secondary current do I have?
Am I doing so the kVA is the 50 kVA at 480? Sorry,
No, yes.
408? 408? Is it supposed to be 480?
Oh, oops. Yes.
Is it 100? It's like 104 then? Because I think I just did my math wrong. So 50 kVA, which would be like 50,000 volts.
That would be 50,000.
And then divided by 480, so it's 104. But then on the other side, you would still do the 50. Yeah, I jacked that math up. And then the other side, you would do the 50,000 divided by 240 for 208. So at the end of the day, it should be doubled.
It should be doubled, yes. I was hoping you would realize that. Since the voltage is going in half, the current's going to be doubled.
Okay, sweet.
And that's reflected up here. Voltage is going in half, current is going doubled. And that's essentially the concept that Westinghouse was trying to do. Now, granted, he was stepping everything up to go distance and then would step everything back down if he needed to. Or even step it up and just run everything at, I think he had 240 back then. But that was the idea, was he was able to get a lot higher voltage with a lot less current, which means he didn't have nearly as much voltage drop or heat loss. Okay, I'm going to run ahead real quick to heat loss. So heat power is considered I squared R, and that's essentially heat. Like you are losing this to heat. So if you're losing voltage to heat loss, then you're not going to have as much power at the end of the run. And if that doesn't make sense, just data dump that for a second and we will keep on going. All right, so this is what the normal transformer looks like. Okay, and these work with this concept. Okay, so if you, and I'm terrible with this, but I wanted to throw it in there for the college kids or whoever else may be seeing this. If you have current flowing in one direction, in this case, the direction of your thumb, the force, the physical force on this conductor or whatever it is going to be in the direction of your middle finger. A lot of this concept is you can equate it to like a rail gun. Like you literally have a conductor with a chunk of metal on top and you apply a stupid amount of current and it shoots the chunk of metal off. And you go on YouTube, watch all the rail guns. That's essentially how that works. Physics speaking wise, if you've got current flowing from this side of the battery, because the small bit versus this large bit, the small bit's always going to be the negative side.
Mm-hmm.
You got current flowing from this side, you're going to have a field going in this direction as the arrows, and so on and so forth. Same concept here. You've got current flowing that, the field's going to be going in the opposite direction, the magnetic flux, if you want to call it. So what that means is every time you have a positive sine wave, the positive part of the sine wave coming in here and going down all these coils, you're pushing electrons this way. Does that make sense? And then when the negative side hits, it's going to go in the opposite direction, which I'm not going to draw because of time.
Okay.
What this is doing and how this works is it's pushing electrons this way, creating a field on this half of the transformer. That field interacts with the coils, and that's what induces current on this conductor, on these conductors. There's a whole lot of GIFs out there, a whole lot of YouTube videos. In short, that's what that is. And if you're not tracking, it's not really important. But the concept is when you have change of current on this side, you'll have equal and opposite change current on this side if it's a 1-to-1. If it's 2-to-1, going back to all this stuff. If you're not tracking that, go to YouTube, watch a couple videos, put it that way. So this transformer concept can actually be applied to motors. Okay. This is a DC motor, meaning it's just got current flowing one way. And then this is an AC motor, which means it has positive and then negative here, negative and then positive here. Okay. You can actually see it right there. You can see those little arrows moving. I'm hoping you can see it.
Yeah.
So the reason these two are red is because, so it's going to be pushing it away. By the same token, this is pulling it. This south pole is pulling this northern oriented pole towards it. And then once this gets far enough, it's going to become a northern pole just because of how this rotor is wired, so on and so forth. So it's basically using both attraction and repulsion to turn this motor. I'm going to hit it again so you can see it. And when it goes white, meaning it's not oriented either way. And this will come in handy here in a second. All right.
Cool.
This same concept, instead of having these this type of rotor where it's got to sit there and switch back and forth, automatically happens in an AC circuit. Okay, you don't have to, this brush is touching this rotor constantly, which means the alternating charges for this part of this rotor is constantly changing. And that's how it sits there and turns. Because you got positive and negative and positive and negative, and it's creating different north-south fields here, pushing and pulling away from the south-north poles. And you may have to watch that a couple times, go back and rewatch that to track it. But for the continuation of our conversation, I'm going to keep on moving. Just the understanding of basic motors, that's what I need you to have so that we can keep going on to 1-pole, 2-pole, and 3-pole circuits in the next lesson.
Okay.
From a physics standpoint, it is very similar to a bicycle. Like you can think of like one sine wave as in 1 foot of the bicycle. Obviously, you've got 2, but setting that aside, when you're starting out at the top, you're starting at 0. And as you pedal forward, the most potential you have, which is at the peak of the sine wave, is going to be right here.
At 90 degrees from start.
Exactly. And as you round out, you're going to end your potential there at 180, which is straight down. Now, if you have clamps or cleats or whatever they're called, you can actually lock your foot onto this pedal. And I didn't know this until recently, like a couple of years ago. But instead of only being able to push down, you can actually pull up on the backside. I didn't know that was a thing because I'm not a bicycle
That's pretty
rider.
cool.
Yeah. So all the professional people,
That's how they go really fast.
That's how they go really fast. And if you ever sit there and watch somebody in traffic and they don't put their feet down, it's because they're clipped onto the pedals. It's not exactly easy to unclip these every single time. But on the upstroke of your leg, that's essentially what this part of the curve is. All right. We're getting up there. All right. So doing slight recap. So wattage or watts is also known as work in the mechanical world, power in the electrical world. Power can be expressed actually several different ways, but these are the 2 most common that I use: VA or I squared R. And I couldn't do the I squared part in Bluebeam because I don't know how to do that. Yeah. So when you're looking at I squared R, it's normally understood you're talking about losses, specifically heat losses. When you're looking at VA, you're looking at power, like useful power that you can use, pumping water up a hill, or brightness of lights, or something to that effect. How much energy can I get out of this? Whereas this one is normally associated with how much energy am I losing in this circuit.
Okay.
So as you can see in this concept, if I can increase voltage, I get a squared decrease in current because of, in the power loss equation. So that's why I want a higher voltage, because I get less loss, I squared R loss, in my circuit. Westinghouse understood this. He had the math. That's why he had to purchase so much less copper to keep the voltage drop down, keep the heat loss down. That's why Westinghouse won. He didn't have to purchase nearly as much copper as what Edison had to, because he was operating at higher voltages, able to go greater distances, and able to have multiple different loads based on whatever voltage they needed, versus Edison was only really able to do a certain DC voltage. I know that I've gone through a lot, and I'm hoping you're able to go back and watch the professor YouTube video that I showed you, the magnetic ripper, to go back and go through this video again on your own time. Next week, we'll be getting into single phase, 3-phase, and the differences between the 2, and poles and all that other stuff.
Okay. Sounds good.
Okay. And
I
if
do
we
have
need
2 questions.
Yes, please.
So first, well, I guess it's more of like a statement, but is that why so like, for example, utility, like, you're saying like DC versus AC, like if you're running on AC power, like, you can go longer distances, and you lose less pressure or pressure, right? Is kind of what you kept saying. I don't know if I'm saying that right, but
sorry, go ahead.
No, you go.
So you have a lot less loss, is essentially a heat loss and voltage drop, when you're running at higher voltages.
Gotcha. Hence why they go like the what are they called? The biggest one, like in the pictures you're showing, like where they're when it's not utility. There's another, like when they're going from plant to plant, like they're going at like extremely high voltage, um, because like that's the best way they can get power from one place to another. Yeah, there it is. That's the word. Like they're getting power from one place to another without losing
A lot of
power, meaning like the heat loss that's coming from it. Is that correct?
That's correct. Yes,
Okay.
they're losing less energy at the higher voltages because they have less current going through the conductors.
Okay. At the end of the day, like even with AC, you are still losing energy. You're just not losing nearly as much.
Exactly, because they have less
Okay.
current.
Okay. Hence why, like, is that why, like, it goes in, I don't want to use the word stages, but like you're going from, here's like the transmission lines are like really, really high voltage, and you're going to like the next one that is still high voltage, but it's not as high, and you go down and down until you get to like a reasonable, like lower voltage, which is still, it's still higher, but like it's lower voltage in the grand scheme of, does that, I guess you get where I'm trying to like go with it.
Yes, no, that's very accurate actually. Um,
Okay.
it all has to do with the quantity of current, quantity of electrons flowing through the conductor. So if I can minimize that, where I've got a couple of milliamps or 1 or 2 amps going 500 miles, I'm going to have a lot less energy loss at that high voltage, low current, 500 miles, than I am at these lower voltage, like 12470, when I'm pushing 60 amps down this conductor to the house. Because these distribution lines, they'll go for 4 or 5 miles at 12470, 35 kV, stuff like that. And then between substations, which you will see around, and uh, just basically terminal stations. I know them as something different. This is going to be the higher voltages, and this is going to be the highest voltage
Gotcha. And
because
then, oh, you go.
these are going to be the longest distances. A couple 100 miles. Several dozen miles, maybe 100 miles here, and then these are going to be 4 or 5 miles.
Like in your residential
Exactly.
areas or whatever.
Yep.
Okay. Cool. That makes sense. And hence why hence why our utilities are the way they are because of AC, because of if that was never discovered, which it would eventually, I feel like at the end of the day everything gets discovered, like we wouldn't be where we are today utility wise if it wasn't for that guy that I already forgot his name.
Westinghouse.
Yeah.
Yes, that's completely accurate. Westinghouse knew that if America was going to adopt electricity, he had to be able to run several hundred miles, and you can't do that at DC. I mean, you can, but it'd be very impractical. Trying to step up DC is very hard to do. Not impossible. Like we do it pretty commonly, but especially way back when in late 1800s, like going from 24 volts DC to 60,000 volts DC, you're not going to do that. Like that would be even hard nowadays. Not, setting aside all the additional problems that come with like conductors and whatnot. The idea of I need to go a couple 100 miles. AC is literally the only way to do that at the moment.
Gotcha.
Tesla had some really cool ideas, which we're not going to get into in this class. But if you ever get bored on a weekend or something by yourself, go Google Tesla and watch YouTube videos. He's really smart because he was trying to come up with wireless electricity.
It's actually, it's funny you bring up Tesla because my second question has to do with like with electric vehicles in the sense of like, okay, we have we we have the different types of like we have the different types of chargers that are out there, and I could be wrong with saying this, but I'm assuming like we have the DC fast chargers, which are the ones that power up your vehicle super fast, are all other chargers still AC, and that's why they don't charge them as quickly? Like I'm assuming you know the answer, but like one, why are we switching to DC if it's so inefficient, I guess, even though yes, it's quick? Like we're
So
still do you does that I guess do you get like my question?
I do, and that's a really great question, actually. So, are you familiar with the term economy of scale?
Not really.
Okay, and that's fine. Um, Actually, I won't even go down that rabbit hole, so it's fine. When we are talking short distances or portability, DC is actually more efficient by a long shot, like way more efficient. Okay, short distances or portability. Now, when it comes to EV stuff, so you've got level 1, level 2, which are AC, meaning you put AC voltages into the rear end of your car. Your car takes that AC and rectifies it to DC to put into your DC battery. So for the record, there are no such thing as AC batteries. Level 1 and level 2 are AC into the car, it rectifies it in the car and puts DC current into the DC battery. When you're talking about level 3, DCFC, DC fast charge, you're actually pushing DC current into the tail end of your car directly to your battery. The reason these are so much faster is because rectifying AC to DC happens outside in this equipment, and it can push a lot more current because the rectifiers are larger into your battery. Whereas here, you can't have stupid large rectifiers in your car because that's just a waste of time, energy, and space.
Okay. But it's so I think when it comes to the EV stuff, like with what we're looking at, like the reason why the DC fast chargers charge, well, apart from it saying fast charge in its name, like the DC chargers are so much faster because it does the change from because at the end of the day, the source is from AC power because obviously that's how we do our that's how our utilities run. Because it's going from AC to DC power, it's doing it before the vehicle so it can push a whole bunch of current through like to the car immediately apart from in the vehicle it's getting AC and has to convert it in the car.
Yeah. Okay, let's do this. All right. It's going to be 1 and 2.
And I know like the electric vehicle is like the smallest little sliver of
Oh, you're
what
fine.
we see, but
All right. So, oh, and this is forward. Okay. So, all right. So type 1 and type 2, you have AC going in, right? AC voltages.
okay.
The rectifiers here to change it to DC are much smaller because they're on board the car. They can't be nearly as large.
Okay.
So the rectifier on board cars are the limiting factor of how fast you can charge the actual battery.
Okay.
Now, and that's because you're pushing AC to it, you have to use the onboard rectifier. However, if you take the rectifier out of the car, you can push a lot more current, a lot more energy. We'll call it energy. You can push a lot more energy to the car itself because the rectifiers can be much, much, much larger in physical size. Like physical size, physical weight. The larger the rectifier, the more energy you can push through it. Or if I've got a larger rectifier, more energy, but I don't want that large rectifier on the car, so I pulled it off. And that's where we get type 3s from. That up a little bit.
So the rectifier is the converter?
Yes.
Okay, it's what's converting AC to DC.
Correct.
Okay.
Didn't use the right word. So there's inverters and there's rectifiers. When you're going AC to DC, it's a rectifier.
Okay.
At least that's what was taught to me. So before I forget, because there was something you had said on the car chargers. There we go. So yes, you can use single phase 120 on the level ones, which is your normal receptacle outlet, whatever's in your house. Level twos are usually single phase 240, which we will get into next round, which is 2 poles, but still called single phase. 3 phase DC fast chargers. Yes, you have 3 phases of AC coming in, but you only have 1 current going out. There's no such thing as 3 phase DC current. Okay, because it's just 1 current going out.
Okay.
That's, like I said, I like that picture right there because it's showing literally right here 3 phases going in, being rectified into a single DC, and then this is the DC cleaned up. They just added a couple capacitors and whatnot. But yeah, this is not 3-phase DC. This is just
DC power.
Exactly. There is no such thing as 3-phase DC, to my knowledge. Okay. Do a quick recap then. Like I said, I highly recommend at some point in time going and watching this dude. This is what the video looks like when you first click on it. It's roughly 18 minutes long. It's amazing. If you don't catch everything the first time, go back and watch it a second time. That, and like I said, if the conversation about this stuff doesn't make sense, let me know. I can totally do all of this stuff again in a better, more formatted, more in-depth means. It was just the idea of this is why, and this is why we use AC, and this is the basic concepts, specifically because I know that you're going to be using this type of math.
The way it works is actually really cool. I'm not gonna. I thought you were gonna cut it off like right after, and I was like, this got really. Not saying it wasn't interesting before, but I'm like, this concept I think is so cool.
Yeah.
Like the understanding as to why we use AC versus DC is awesome. And then now that I did ask that question, I get why they're trying to get, for example, like electric vehicles charging DC because it is more efficient doing it that way because there's, like you said, less distance. And then if there is a way to convert something to DC for charging purposes or whatever, as long as it's a short distance, it makes sense. But like at the end of the day, the reason why utility is the way it is because that is the most efficient way to do it without losing a whole bunch of work, power,
Energy.
you'll lose heat, energy. Okay, the energy.
Yeah, because remember, P, power, or energy in our case, is equal to I squared R. So if you're, and that's associated with loss, like heat loss, but I squared R is energy loss if you want to look at it like that. And the higher the current, the more loss you got.